section 9.7, Pascal's formula and the binomial theorem. Basically, we discussed all these topics before. Therefore, let us switch back to one of our previous sections. And this section is section 5.1. So in section 5.1, we introduced for the first time the choose symbol. Let us go over the properties once again. So it is easy to prove that n choose 0 is equal to n choose n is equal to 1. We just use the formula. N choose 0 is n factorial over 0 factorial times n minus 0 factorial. Keep in mind that 0 factorial is 1. It's not 0. It's 1. We cancel out n factorial, the result is 1. In the same way, we prove that n choose n is 1. Similarly, n choose 1 is equal to n choose n minus 1 is equal to n. And again, we use the formula. In order to find n choose 1, we apply the formula. And now, in order to simplify this formula, we do the following. N factorial is n minus 1 factorial times n. We cancel out n minus 1 factorial, and the result follows. Similarly, in order to show that n choose n minus 1 is equal to n, we apply the formula first, we simplify this expression, done, and then rewrite n factorial as n minus 1 factorial times n, and after the cancellation, we get n. In general, n choose k is equal to n choose n minus k. So note that this formula generalizes formula number 1 and formula number 2. If k is equal to 0, we get 1. If k is equal to 1, we get 2. But now let us prove this result in general. So n choose k is equal to this. It's the formula. Obviously, we can switch positions of these two terms in the denominator. After that, observe that k can be rewritten as n minus k, which is by definition of the choose symbol, n choose n minus k. By the way, it is a little bit easier to prove this formula if we go not from the left to the right, but from the right to the left. Because the jump from here to here is a little bit tricky. You have to understand first that k should be rewritten as n minus k. However, if you go from the right to the left, it's almost a no-brainer. The jump from here to here is the formula, and then we simply expand parentheses and cancel out the common term in order to jump from here to here. All we need after that is just switch positions of these terms and apply the formula. Next, this formula, it's even harder to prove. Again, here's what we do here. We apply this formula in order to jump from here to here and from here to here. In this case, r is equal to k minus 1. In this case, r is equal to k. Done, done. Now we have two fractions with different denominators. Therefore, the next step is to come up with a common denominator. In order to do that, in fraction number 1, let us multiply top and bottom by k. In fraction number 2, let us multiply top and bottom by n minus k plus 1. After that, observe that k minus 1 factorial times k is k factorial. Similarly, n minus k factorial n minus k plus 1 is n minus k plus 1 factorial. Note that now we have the common denominator. So we add up the tops. Done. Next observation. Note that we have a common term, n factorial. We factor it out. After that, we cancel out the common term, k. Done. And last observation, n factorial times n plus 1 is n plus 1 factorial. Very last thing. Let us rewrite minus k plus 1 as plus 1 minus k. And now the jump from here to here is the formula again. R is equal to k. And we are completely done. Here's a nice application of the formula above. Let us prove this identity. Once again, one way to prove this identity is to use the formula for choose symbol. However, it's much easier to use property 4. This property, observe that 2 times n choose k can be rewritten as n choose k plus n choose k. And by property 4, this sum is equal to n plus 1 choose k. This sum is equal to n plus 1 choose k plus 1. Lastly, by the same property, this sum is equal to n plus 2 choose k plus 1. And we're done. Now, let us discuss another nice application of the choose symbol. Let me scroll down to the appendix. Please take a look at this. Here we expand parentheses. X plus 1 to 0 power is 1. X plus 1 to first power is x plus 1. X plus 1 square is x squared plus 2x plus 1. X plus 1 cube is x cubed plus 3x squared plus 3x plus 1. And so on and so forth. Question is, how do we come up with, say, this formula? Do we just write x plus 1 to 10th power as x plus 1 times x plus 1 times x plus 1 and so on 10 times and then expand parentheses? Yes, this is one way to come up with this formula, but it takes unnecessary long to expand all parentheses. I say unnecessary because there is an easier way to come up with the same result. Please take a look at the following. Compare, for example, this row and this row, this expression and this expression. Observe that the coefficient in front of x to 5th power is 1. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. Similarly, let us compare, say, this and this. 1 plus 8 is 9. 8 plus 28 is 36. 28 plus 56 is 84, and so on. So, if we know coefficients in the previous formula, it is easy to come up with coefficients in the next formula. And observe that what we do here is kind of similar to property 4. Here we have the sum of 2 consecutive choose symbols. I say consecutive because here k minus 1, here k. We get this. And now think about the following. If we think about n as about a row number or power in the expansion of 1 plus x to nth power. Here it looks like, but it has to be proven. We have two consecutive coefficients. We add two consecutive coefficients when we expand x plus 1 to nth power, and we give a coefficient of the expression when we expand x plus 1 to the power n plus 1. Now let us restate this result in the following rigorous way. We call it the binomial theorem. X plus y to nth power is equal to this. Or, in expanded form, x plus y to nth power is equal to n choose 0 times x to nth power. By the way, observe that n choose 0 is 1, plus n choose 1 times x to n minus 1 times y, plus and so on, plus n choose n, y to nth power. Okay, let us talk about the following. How would you prove this theorem?
Prove by induction.
Okay, one way is to prove it by induction. We will discuss this method, this way of proving this theorem. My question is it possible to prove this theorem, or at least to explain somehow why we have this formula without induction? Can you come up with a combinatorial proof?
I was going to say it has something to do with the combinations.
Combinations. Okay. Indeed, choose symbol gives us the number of k combination. But what's the relationship between this algebraic formula and combinations?
If you look on the Pascal's triangle thing, it's basically the same thing.
Excuse me, give me a second. So, first of all, since you mentioned Pascal's triangle, let me explain to everybody what is Pascal's triangle. Pascal's triangle is the following. The top number is 1. Next row, 1, 1. Next, 1, 2, 1, 1, 3, 3, 1, and so on. In other words, in order to obtain the next row, we add coefficients from the previous row. But how to know that the resulting coefficients will be coefficients of this expression after we expand it? Why is that?
I think it maybe has to do with there's a number of combinations of, like, for x cubed, there's 4 combinations, or there's the number of combinations is 4, or possibilities, and for x squared there's 6.
Okay, so you're talking about combinations. Combinations of what out of what?
Oh, I forgot what the rule was for that table.
No, the rule is clear. 6 plus 15 is 21. This is the idea of Pascal's triangle. Big question is why? If we apply this rule, we will get coefficients. You see?
It's from the thing you went over in the last PowerPoint, the rule that you proved
Are
before.
you talking about property 4?
Yes, yeah.
But note that in order to use property 4, we have to use the fact that coefficients are choose symbols. But this is what we're trying to prove. Indeed, if we know that the coefficients are the choose symbols, we can use property 4. But we don't know it yet. We have to prove it.
Right, okay.
So let me start with the second version, version number 2 of the proof. Please take a look at this. Let us consider the following product. x1 plus y1, x2 plus y2, and so on xn plus yn. Let us expand all parentheses. If we expand all parentheses, we will have 2 to nth power terms. For example, we expand parentheses here, we have 4 terms. In general, here 2 to nth power terms. Why?
Because each term gets multiplied by 2 terms, but there are n terms, so 2 to the power of n.
Can you use the multiplication rule and combinatorics?
Yes, using distributive property, you have to either do x1 times the other stuff or y1 times the other stuff, right?
Exactly. So basically, we have n positions, position number 1, position number 2, and so on, position number n. For each position, we have 2 possibilities, either xi or yi. For position number 1, we have either x1 or y1. For position number 2, we have either x2 or y2, and so on. For position number n, we have either xn or yn. Now, when we expand parentheses, we basically select from each position only one of these terms. Here, we choose either x1 or y1 times. Here, we choose either x2 or y2 times, and so on. Here, we choose either xn or yn. So we have 2 possibilities here, 2 possibilities here, and so on, 2 possibilities here. Therefore, the number of different terms will be 2 times 2 times and so on times 2 to nth power. Here is what we do next. Note that over here we have x plus y times x plus y and so on times x plus y. In other words, x1 is equal to x2 and so on is equal to xn, and y1 is equal to y2 and so on is equal to yn. If we expand all parentheses here and replace all xi's by x and all yi's by y, the terms will be equal if and only if in each term the number of x's is same, or equivalently the number of y's is same. Suppose in some term we have k x's and therefore n minus k y's. This means that each time when we select one of the terms here in order to expand parentheses, we choose in total k x's out of n possible x's, or equivalently n minus k y's out of n available y's. But in how many ways we can choose k different x's out of n available x's, or equivalently n minus k y's out of n available y's. In n, choose k ways, or equivalently in n, choose n minus k ways. Okay, now let us go over the proof by induction. For n is equal to 1, this equation becomes x plus y is equal to 1 to 0 times x to 0 power y to first power plus 1 choose 1 x to first power y to 0 power. Clearly, 1 choose 0 is 1. 1 choose 1 is 1. This expression becomes y. This expression becomes x. Obviously, x plus y is equal to y plus x. Step 1 is done. We just showed that this formula is true for n is equal to 1. Next, assume that what is written here is true for n minus 1. Let us prove it for n. So, x plus y to n's power is x plus y times x plus y to n minus 1. We use inductive step. X plus y to n minus 1 is equal to this. Now let us expand parentheses. We multiply this expression first by x, so instead of k's power, we get k plus 1 power. And now let us multiply this by y. Instead of power n minus 1 minus k, we get just n minus k. Here is what we do next. Let us replace in the first sum k plus 1 by I, and in the second sum k by I. So if we replace k plus 1 by I, this becomes I, minus 1 minus k is same as minus k plus 1, but k plus 1 is I. So this expression, the power, becomes n minus I. Lastly, since I is k plus 1, k is I minus 1. We replace k by I minus 1. And here we start from 0. But if k is 0, I is 1. Here we put 1. If k is n minus 1, I is n. Here we put n. Note that this sum can be rewritten in the following way. Sum from 1 to n minus 1. It's exactly what is written here. Plus the very last term when I is equal to n. But when I is equal to n, this becomes n minus 1. And n minus 1 choose n minus 1 is 1. If I is equal to n, this becomes x to n's power. So in other words, what is written here can be rewritten as sigma of this plus x to n's power. Similarly, let us rewrite this, the second term, as this sum from 1 to n minus 1. It will be this, plus the first term, when I is equal to 0. But when I is equal to 0, the whole thing becomes y to n's power. Lastly, by property 4, this is equal to this, and the whole theorem is proven. Any questions here?
Can you go through the steps of the induction again?
This is just a version of induction. So if we use our previous style, we have to do it in 3 steps. Step 1, for n is equal to 1, this is true. Step 2, assume that our formula is true for sum n is equal to k minus 1. Prove that it is true for n is equal to k. Or step 2, assume that it is true for n is equal to k. Prove that it is true for n is equal to k plus 1.
So this one you did k minus 1, then prove k.
Yes, if we convert it into steps, in step 2, we assume that our formula is true for n is equal to k minus 1. In step 3, we prove it for n is equal to k. One application of this formula, guys, please take a look at this really nice result. The sum of all consecutive 2 symbol is 2 to n's power. N choose 0 plus n choose 1 and so on plus n choose n is equal to 2 to n's power. we use the binomial theorem. Observe that if in the binomial theorem we replace x by 1 and y by 1, the left-hand side becomes 1 plus 1 to n's power, which is 2 to n's power. The right-hand side, in the right-hand side, x to k and y to n minus k will disappear because x is 1 and y is 1. It's exactly how we obtain this result. Once again, you replace in the theorem above x and y by 1, we get this. The left-hand side is 2 to n's power. Here, all these terms disappear. Done. Similarly, in order to prove this result, in the theorem above, we replace x by 1 and y by -1. The left-hand side is 0, the right-hand side is this. And we are completely done.